How does the red planet connect to biochar? Today on the Biochar Show, I am joined by Dr. Toufiq Reza, Associate Professor of Chemical Engineering at Florida Tech, a leading voice in hydrochar research and one of the scientists exploring how carbon materials could help us grow food on Mars. His team is working with NASA to understand what it takes to turn Martian dust into a living, plant-ready medium. In this episode, we dig into hydrochar, biochar, remediation, and how circularity in space agriculture can reshape the way we think about soils here on Earth. Taufik's curiosity and his enthusiasm are absolutely contagious, and I think you'll walk away, just like I did, inspired by what carbon can unlock. This is the Biochar Show, where we explore carbon not as a crisis, but as a tool for resilience and speak with the people putting biochar to work in the real world. I'm your host, John Webster with GoBiochar.com. Let's get started. We're here today with Dr. Toufiq Reza, and let's just get rolling into this. And could you go ahead and tell us a little bit about yourself?
Sure, absolutely. Well, thank you very much, John, for inviting me in Biochar Show. I mean, I am Toufiq Reza. I am an associate professor at the Florida Institute of Technology in Melbourne, Florida. And I am a biochar enthusiast. I have did my PhD in thermochemical conversion, stayed around the biochar research, and then continued with biochar research. So, I mean, thank you very much for having me, and be happy to share my thoughts and looking forward to conversation with you.
Oh, it's very much our pleasure. I know it was kind of, you're a very busy man, so it was fantastic that you were able to make time for us today. So I think what I want to do is I kind of want to jump into how is it that you got into science, and from that first spark on the science endeavor, what was your career on? What schools did you go to? I understand that you also have an extensive engineering background.
Yeah. Yeah. No, I was born and raised in Bangladesh, and I did my bachelor in chemical engineering from Bangladesh University of Engineering and Technology. And then I know I worked for an industry for a couple of months and then realized that maybe I should go to higher studies. And that's the time I started applying and ended up in University of Nevada, Reno, where I did my master's and PhD. From there, working on hydrothermal carbonization, and then I was looking into different papers about, what happened with hydrothermal carbonization, introduction with the biochar, and realized that a lot of research is going on in Germany. And at the same time, I got a job offer to do a postdoc in Leibniz Institute for Agricultural Engineering in Potsdam, Germany. So I took that opportunity. I did my postdoc in Germany and then returned to the United States. I was a faculty at the Ohio University in Athens, Ohio, and then moved here at Florida Tech in 2019. So this is, a short journey, but moving around from, Asia to the United States, back to Europe, and then come back to, to the States, and then I'm so glad what I do, and also helping the environment as well as outer space as well. Just putting my footprint everywhere.
Yeah, you're well traveled and well spoken. How many languages do you speak?
I speak let's see. I speak 3.5, I should say, or 3.25. My native is Bangla, my mother language, and then the education is in the U.S., so that was the English, and then I went to Germany. I really wanted to learn German, so I finished what German they call the A1, A2, B1, B2, C1, C2, and D1, D2, and D2 means that you are an expert in German language, and my capability is limited to A1 and probably a little bit of A2. So I know a little bit of it, like when my colleagues started to teach me different words. Of course, they don't start with the good words, so I know a little bit about, I can pick up those other words very quickly.
Very good, very good. Thanks for that explanation. Let's go ahead and jump into So let's explain to the audience what exactly is Hydrochar and because you were talking about HTC. Can you explain that?
Sure, absolutely. It's a pleasure. So HTC, I'll tell you a little bit of a background of HTC and how the name come through, in my opinion. So HTC refer to hydrothermal carbonization. So we have the name hydro, and we have a thermal and a carbonization. So hydro is basically it is happening underwater. Thermal means it is happening at higher temperature and higher pressure. Carbonization means it is densifying the carbon. Basically, what it's doing is simply put a pressure cooking of a biomass substance. So you probably have a pressure cooker at home, and you probably have noticed that if you put a sturdy material or maybe a good beef, and it could cook a little bit easier, that's because it is cooking at higher temperature and higher pressure. So the hydrothermal carbonization is, you can think of as a large pressure cooker, and then it cooks over there, and then it produces also a solid material which we call hydrochar. And I'm going to give you a little bit about background, because when I started my PhD back in 2009, when this field is also evolving and we were trying to come up with a good name. In our group in University of Nevada, as well as Kent Hockman's group at Desert Research Institute, so we were initially calling it as a wet torrefaction, because the temperature was similar to a torrefaction, about 180 to 250 degrees Celsius or so, but it is happening at water environment. So we used to call it as a wet torrefaction, a wet torrefied biochar, and then hydrothermal liquefaction come in, and then we said hydrothermal liquefaction that produces the liquid fuel. Maybe it is hydrothermal carbonization, which produces a char, which is not a biochar, so it is a hydrochar. So that's how probably the name come in. And again, at that time, it was a couple of groups working on hydrothermal carbonization. Our group, Kent Hockman's group, Maria Magda Titirici and Marcus Antonetti from that time, they were in Germany, and then Axel Funke, Judy Libra, they were in Leibniz Institute. So and then Peterson and Tester, they were working over here as well. So I think over the time it evolved as a hydrothermal carbonization, and the char become hydrochar.
Yeah, thank you for that primer. That's fantastic. I guess well, don't you have a little sample you can show us so we know what it looks like?
Yeah, absolutely, absolutely. So yeah, this would be a hydrochar. As you can see, it's not as dark as biochar. If I look into next biochar and hydrochar would be a little bit lighter material, and that is probably related to the a lower temperature that we would usually use compared to pyrolysis. As you probably know, pyrolysis happens between 400 to 800 degrees Celsius, but hydrothermal carbonization stops at about 250, 260. After that, it is turning to be hydrothermal liquefaction. So that's one of the reasons. And also the color could come from not as much as carbonization as we usually do for biochar, and also the functionality comes in to play as well. So that's why, usually if you see hydrochar would be a little bit lighter color, brownish color, but if you see biochar, it would be usually very dark, unless you have something else, an unusual feedstock in biochar.
Yeah. So I guess I have a question, because you showed the two next to each other. So color is one difference. What about that cell structure, the pore structure inside?
Oh yeah, it's not. This is the two different solid material. Okay, so and they're different in many ways. So the way they're made is different, and also the properties are different. So biochar is more porous, and it also has a structure. Hydrochar is less porous. It is mostly you can think of as a spherical particle and it has a hydrophobic core and a hydrophilic functionality. Hydrochar has a lot of functionality on the surface to it. And biochar, depending on, I mean, especially around like 600 degree to 800 degrees Celsius, it has a very lower kind of like a functionality, but more porosity. In terms of like putting into numbers, in general, hydrochar, we are thinking about like less than 20 meters squared per gram, where you probably know that a good biochar would have about like 400 to 800 meters squared per gram. So morphology is different. Carbon content wise, biochar would have usually from the same feedstock, biochar would actually have more carbon than hydrochar. But in terms of functionality, and I'm talking about oxygen functionality, hydrochar would have more functionality. And again, these are two different chars which comes with two different types of applications depending on what you want to do.
Yeah. What's the difference in the weight between the two and maybe the pH?
Yeah, so the pH of hydrochar would be a little more acidic, and the pH of biochar would be a little basic. So that's the pH difference between them. But again, I mean, depending on where the feedstock is coming from. But I'm comparing that if the feedstock is the same lignocellulosic biomass, this is what we would be doing. Depending on where it is applied as well, if you are talking about hydrochar, it would be usually applied for functionality driven separations. So where I can actually use my oxygen functionality to capture targeted chemicals or toxic materials or chemicals as well. Where biochar, mostly it would be like a pore driven principle. So the targeted chemical would actually go into the pore trapped on it. So that would be the usual difference between these two.
Okay. In terms of the application, are you implementing this into products like other physical products or different types of agriculture or specialty? What are the specialty applications here?
Yeah, no, absolutely. So yeah, in terms of the hydrochar, we are applying it a couple of different places. We are applying it for agricultural purposes because we are converting animal manures like dairy manure, swine manure, poultry litter into this hydrochar and then apply it to the field to actually see the germination index and how we can grow different feed and different plants material to it. We have also used hydrochar for water treatment, what happened if we have methylene blue as well as other toxic contaminants like harmful algal bloom toxins, how to separate that as well.
So, Taufik, I was wondering, what are the different applications? Because you have the biochar and then your specialty with HTC, the hydrothermal carbonized material. What's the difference in the application opportunities?
No, absolutely. So when I started my PhD, the sole focus of my PhD is to try to make a solid fuel from loblolly pine using hydrothermal carbonization route. And then I used to show the pretty cool picture and saying that the way coal was made underneath the earth, it took 1 million years to actually high pressure, high temperature, densify it into making coal. So can I make it in 5 minutes inside of a reactor? So that's basically that. It took the Mother Earth 1 million years. Can I do it in 5 minutes? So that's basically the way to do. And of course, it works. And then most of the hydrothermal carbonization research had been targeted for the fuel. So hydrochar being a fuel. And then we usually target the low calorific value feedstock like municipal solid waste, food waste, as well as agricultural residue, and convert it to a coal-like feedstock that has a calorific value similar to subbituminous coal, etc. So, and that's what we did when I was a PhD student. But then gradually exploring more more application of hydrochar. So it is not only a solid fuel; it is also much more valuable as a filtration media, as well as a functional media. So and that's what we have been exploring it, and of course, it looking into from like if I have high nutrient feedstock like a dairy manure, swine manure, it has decent amount of nitrogen and phosphorus. So by hydrothermal route, can I actually capture that nutrient? So nutrient recovery has become a big part of our research by looking into it. Now, in terms of comparing with biochar, biochar has mostly been used as a soil amendment as well as carbon sequestration. But again, I mean, in my group, we do a little bit of exploring other applications of biochar, like for example, biochar for water purification, biochar for harmful algal bloom remediation, etc. And then, yeah, I mean, did I ever connect those two? Absolutely. So I did make, I did hydrolyzed hydrochar, and this is actually making the product much more interesting as well, because biochar has a lot of porosity. Hydrochar has a lot of functionality. So if you do pyrolyze the hydrochar, it has then both. So I have both the functionality as well as the porosity. That would be more important for targeted application. For example, toxin removal from water column, as well as carbon capture or gas separation. So a little bit long answer, but I just wanted to
That's
lay it out.
yeah, and you know what? That's totally okay. So some of the questions I know that will be asked is, what volume of material? So what volume of material do you need to make 1 cubic foot of HTC material? Because with pyrolysis, we're usually talking about a 3 to 1, maybe. So what is it with HTC?
The HTC would usually be 2 to 1, but it would also depending on the feedstock. But usually when we're talking about lignocellulosic feedstock, it would be 2 to 1. So the mass yield would be around like 50% or so. But yes, you're right. For the pyrolysis, we could go all the way to mass yield about
Yeah,
25%.
yeah. What does it weigh?
What is the weight?
Yeah, what's a weight of like a 5 gallon bucket or 1 cubic foot of the material?
So I mean, talking about density. So hydrochar would be higher density than biochar. So the bulk biochar is pretty light, but hydrochar
Hmm.
would be very dense in terms of. And then we also did some study on further densification, and if you can make pellet of hydrochar, you can actually pack a lot of energy into one of the hydrochar pellet, which can be actually used as a solid fuel, like for home
Hmm.
cooking, as well as the home heating different purposes. So that is one way, and if we can, if I remember correctly, we could actually dense and make the pellet around like 1.4 1400 gram per cc, so it would be like heavier than water,
Yeah,
and the energy density become as close as like a bituminous coal, like about 35 megajoule per kilogram, densely packed fuel at that point, but after densification.
that's wild. Hey, I know that there are some systems that'll take densified materials, so pelletized material,
Mhm.
and then convert that into biochar. So could you utilize some of the calorific value and then still have some biochar come out the back end of a
Yeah,
system?
no, absolutely. You can definitely do that. So we started with the pelletized hydrochar, and then pyrolyze it to make biochar. Our group didn't do it, but I have seen many paper. They actually went into that route as well, and just the reason just you explained to it, because we can actually feed into a lot into a pyrolyzer, and then get a lot of value out of it. And then the biochar usually has a shape of the biomass, and we
Hmm.
usually don't lose the shape. So if you can think in that way, that I saw I think there was a couple of years, I think a couple of years ago, I guess, people were introducing in the US as a black pellets. So those are going into the similar direction. So you first make the pellet and then torrefy it or pyrolyze it. So I've seen people do a similar research actually to actually get a shape of it, because if you have a pelletized shape, it is easy to transport and apply as well. So that's a good way to do it.
Yeah. So when you're doing the HTC with things like manures and municipal solid waste, all these different residues, especially the animal manures, does that then qualify as fertilizer because there's more nutrient retention and holding in there?
Yep, yep, yep. So yeah, it is. So the nutrient content actually densifies inside of hydrochar, and mostly phosphorus would actually be densified inside of hydrochar, and then that makes a good phosphorus rich fertilizer. We also have seen nitrogen and potassium that can be added to the phosphorus as well, by tweaking hydrothermal carbonization process a little bit, playing the or tuning the parameter. But yeah, I think it's possible. One of the thing that we are now trying to do, if I think in this way, that the hydrothermal carbonization process is evolving and emerging, but we're still a little bit falling behind the pyrolysis and biochar. So we're catching up, but we were still falling behind. Like, for example, one of the biggest thing is, you asked the question about the fertilizer. I can do the testing in the lab, and then I can do the nutrient content of it. So it is valid, but then how would it perform in a field? This is where we are going now. So in a small pot, we have studied it, but now we need to take it to a large field and then do a demonstration for multiple years, because biochar, the half-life of hydrochar is much lower than the half-life of biochar, so it is not as stable as biochar. So we need to look into, like, okay, if the stability is not high, how frequently we should be using hydrochar as a fertilizer.
Well, tell me you haven't thought about combining the two of them together, biochar
Oh
plus
no, absolutely,
hydrochar,
I
and
thought
that's it.
about it.
Yeah, yeah, into a single
No, no,
pellet or into a mix.
I
Yeah.
yeah, yeah, no, I did think about it, and then of course I do it because to increase the shelf life as well as the half life of hydrochar, we need to do some sort of pyrolysis as well. And also there is another thing: when we make hydrochar usually comes with some furan derivatives like furfural, hydroxymethyl furfural. Sometimes they are not really. I mean, it has good nutrient content, but those furan derivatives are sometimes not good for the plant material. So adding pyrolysis step would actually eliminate those and then make biochar more porous. The carbon become more stable, and all together, it is going to be better for the soil. But then question would come in as like, okay, is it economically viable? Can
Hmm.
we do it commercially? I think this is where we are heading now.
Yeah. So I've been asked to source HTC materials in the past, and honestly, I cannot find any producers in the US. So
Yep.
that does seem like it's going to hold back the commercialization. Are you aware of anyone making larger
Yeah,
systems that are
yeah, yeah.
available
We
in North
are.
America?
Yes, yes. So in North America, there are at least a few entity who has a pilot scale a hydrothermal carbonization reactor, but they are okay. So they're like a SOMAX, SOMAX. They're based off of Pennsylvania. They are trying to convert sewage sludge into hydrochar. Now, the way it works is a little bit differently, because the business mechanism, if I understand correctly, is a little bit different from business to business. For example, many hydrothermal carbonization commercial producers actually look hydrothermal carbonization as a process of waste elimination
Hmm.
rather than making a product. that they can sell for a market. So I think so when we're talking about sewage sludge, this is one big thing that come to my mind. But yeah, I think you're going to see some more commercial hydrochar producers coming in. uh, they talked about Somax. There is Thermcam. They're also bringing Japanese technology to the United States as well as Canada. So they're offering a mobile hydrothermal carbonization unit, which can convert it, and then you probably know that. I mean, in Europe, there are many entities. They actually practice hydrothermal carbonization at various scale.
Yeah. So real interesting is that, you have the biochar tends to run on its own energy when you're doing the pyrolysis. You get it going. So does the HTC have the capacity to generate its own thermal energy in order to run this service or the process? And then if not, is it using natural gas or diesel fuel, or could you literally install a pyrolysis system to feed into the HTC system? So that way you're doing heat capture and creating
Mhm.
benefit from both chains.
Yeah. So uh, the short answer is we so far the commercial entity that I have seen, they needed auxiliary power, and in most cases natural gas would be a cheaper source of energy. But if we're talking about a mobile unit, most likely diesel would be the unit to run it. And then I've seen there are several industry who would actually use diesel or natural gas to heat up the steam, and then that steam would actually feed the heat to the HTC unit. Of course, we can do it. The problem with HTC would be like if you are talking about a batch process, because it runs at 250 degrees Celsius or so. Heat recovery from the batch process is a little bit difficult process. So that's where we usually lose most of the heat. And it produces a gas, but that gas doesn't have that much of calorific value, unlike pyrolyzer gas.
Mm-hmm.
It doesn't produce any condensate like pyrolysis, which we can further burn. So it's only the hydrochar we are producing, as well as a processed liquid, a little bit of gas. So in order to do that, it can be we need some auxiliary power. If you look into a glucose chemistry level, the HTC process is actually an exothermic reaction, a slightly exothermic reaction. It doesn't need that much of power. So once it is go up and running, it would probably be needing a very small amount of power. But there are studies out there who actually did study it, because we're going to lose some energy because it is not perfectly insulated all the time.
Mm-hmm.
So the auxiliary power come in almost all the cases in HTC reactor.
Yeah, I can't help but have that kind of biochar circular fantasy where you have two side by side pyrolyzers that are running, feeding like multiple different HTC systems, and you're just like processing all these biomass and these waste materials and
Yep.
and doing biochar output, HTC thermal capture. It just like that sounds like that sounds like a really fun
No, no,
project. Yeah.
it sounds amazing. It sounds amazing. And this is basically I'm thinking about like a large waste treatment facility,
Mm-hmm.
because for hydrochar, what we would usually prefer the material which already has enough water in it, like for example sewage sludge, dairy manure, and it is very difficult to remove that moisture out, and then run pyrolysis. So that is the process, or that those are the feedstock that would be more appropriate for hydrothermal carbonization. But then if we have like a little bit drier feedstock, like pine and agricultural residue, etc. So yeah, one can feed into other, and then if we have like a regional solid waste feedstock could come into a facility, and then that facility can actually be a net zero auxiliary power facility. It would be amazing.
Yeah.
And we produce the biochar that we could sell, and then hydrochar that we could sell as well. It would be amazing.
Well, if you ever need help selling that concept or implementing a plant, please reach out to me. I think that'd be an amazing project to work
Absolutely.
on. Yeah. Hey, so in terms of HTC materials doing the filtration and also, being able to be sourced by processing sewage sludge, the big question these days is around PFAS. So what happens to the PFAS inside the HTC?
Yeah, very good question. And I get this question more frequently, like what happens. So if you look into it, so hydrothermal process can break down PFAS, but it needs a little bit more temperature and pressure. If the goal is to eliminate PFAS from sewage sludge, we would probably need to run it more than 250 degrees Celsius. So that's the thing. If you can run it a little bit higher temperature for a longer time, it is going to break down the PFAS. But if you for the usual like 180 degrees Celsius or so, it would be difficult to break down all the PFAS compounds, especially the short chain PFAS compounds. So that's my understanding of it. And then the hydrothermal liquefaction community, they would usually claim that at 350 degrees Celsius, where usual hydrothermal liquefaction happen, PFAS breaks down.
Okay.
Definitely, and there are several literature out there confirming that hydrothermal liquefaction scenario in sewage sludge PFAS already.
Okay. What about, so I admire your enthusiasm and just that energy you literally have to build up this HTC industry and your just what you're putting into it. Real quick, what's one kind of built environment product that you can see? So for the human environment, different materials that we have inside our house or our cars, what could you see HTC being incorporated with?
So HTC being incorporated with, as I mentioned to you, it prefers wet feedstock. So anything that you think that are wet, for example, food waste is an appropriate example for an HTC unit, and then also sewage sludge I work with at a small project on septic tank waste. That's basically home sewer treatment system that also worked very well. But yeah, I mean, those are the things that we worked. And in my group, we also looked into hydrothermal technology to break down plastic. And one example I'll give you is HTC works very well to break down PVC. So there's a polyvinyl chloride, at high temperature and pressure, it really breaks down the chlorine, and that actually works very well. And then, so I mean, we studied that one. It makes good solid product that is, not haloginated. So yeah, I mean, those are some of the household items that I think HTC relevant. If you have yard waste and if you have food waste, and if you are actually doing composting, that can also be applicable for hydrothermal carbonization.
Yeah. You know what I want to do now? I want to do a little segue here because we opened
Yeah,
up at the top of the show talking about the red planet.
yeah,
And because
yes.
that's how you caught our attention is because we were noticing
Oh yeah,
some noise about agriculture on Mars. So let's talk about
yes,
that a little bit. So what do you see
absolutely.
as HTC's and biochar's capacity on this planet? Let's talk
No,
about it.
absolutely. Absolutely, absolutely. So yeah, I mean, I need to give you a little background. So
Okay, yeah,
we
yeah.
are in Melbourne, Florida, and from my office window, I can see rocket launch. So
Wow.
we're very close
That's cool.
to Kennedy Space Center. We can see rocket launch. We are over here in Brevard County. We call the Space Coast of Florida. And I also spent a sabbatical in Kennedy Space Center, which was actually eye opener for me because the technology that biochar technology, hydrothermal carbonization, I never thought that there could be applicable or there is a need for it in space, but I looked into them, and then I said like, yeah, there could be a solution. And when I looked into Martian regolith, so I'm going to show you a Mars regolith. So this is a red planet. So that's a regolith. It is made of it. It is different than the soil that we used to see in Earth. In Earth we have soil. We have but there is, if I want to think about what happened in future for astronauts as well as the colony of what we want to do in Moon and Mars, they'll basically be relying on food pouches that we usually send it from the earth over there. It is not sustainable, and you would be surprised to know that sending out 1 kilogram of anything from Earth to Moon or International Space Station, it cost us hundreds of thousands of dollars. So economically, it would make more sense if we can actually start, growing simple lettuce, growing something over there. Now the question is like, why would it grow? And can I actually be doing it? So what is lacking? So that's basically where I looked into it. Like, why isn't it growing in? Why plant doesn't grow in Martian soil? So Martian soil has a lot of iron, some minerals. It does not have nutrient. It does not have nitrogen. It does not have carbon. And then I looked into like, okay, so my biochar has a lot of carbon in it. It is porous. And also if we can make the biochar from human waste in the colony as well as other nitrogen sources, then we can actually add nutrient to it. So this is where it come in. It is actually solving several problems, adding biochar or pyrolysis concept to Martian regolith as well as lunar regolith, completely different soil property we're talking about. But yeah, it can actually solve that problem. We can bring it, and then we have been looking into those property improvement and also germinating lettuce and then small plants, and then actually growing the earth soil as well as what would be different. The goal is to see like how can we make it as a porous material that can actually hold those water holding capacity, increase water holding capacity, so that it can actually help growing plants. So that was one of the goal that we have been working on. We are also, I mean, so far we haven't looked into the microgravity. The Mars has like a 1/4 of gravity, and then Moon has 1/8 of gravity. So what happened if it happened at microgravity? But yeah, I mean, one step at a time. But looking into like, do we have feedstock available to do pyrolysis? So the answer is yes. Human waste. We have the packaging system. We have if somebody is growing tomatoes, etc. So there is a way to actually get that the feedstock for carbon material for biochar as well as hydrochar. But then can we do it in the Mars? So you cannot catch a fire, or you cannot create a fire in Mars, because we don't have that much of oxygen available. Yeah. If we make oxygen, we'll probably be utilizing it for astronauts breathing, not actual trying to combust it. But there would be the case that we have the solar power, the electric power, microwave system is very important as well. So we can apply those to actually get into the pyrolysis process, and then of course in a combination of it and mixing this up. One of the big problem for at least the Martian regolith is the perchlorate. So perchlorate is basically being like leaching it to it, and then that's one of the things that usually don't allow the plants to grow. Adding biochar would actually be help removing the perchlorate. That this is one of our hypotheses that we have been testing. A little bit longer answer, but I'd probably say it's a big problem. And again, I mean, if we can solve this problem, there are lots of things we can do on Earth. I mean, think about why can't we grow plants in like high desert area? And if we know how to grow plants in Moon and Mars, we could probably be bringing that technology to the earth and then start investing on it. Like, how can we do the reverse the deforestation, growing plants in high desert area or area that is similar to those harsh environment.
Yeah. So, a lot of kind of that NASA and space tech tends to come over into the commercial environment. And then, one has to think, well, what are they also funding trials for high desert plant
Hmm.
growing that they can use as
Yep.
a kind of primary step to get up there?
Yep. Yep.
Yeah, that's cool. I always, and it just has me wondering as well as about that biological element in that regolith or the lunar soil, the soil, right?
Yep.
And then
Yep. Yep. Yep.
and
Yep.
Martian as well. So, what I hear when I hear that, the fact that you can bring it into the harsh environment, minds, if you can do it on Mars, if you can do it on the moon, you could certainly do it
Yep.
here and then apply that tech to things like
Mhm.
mine site remediation,
Yep.
maybe even other kind of post disaster events and whatnot in
Yep.
order to
Yep.
create the benefit. So I guess and I do want to point out that there was really recently a fantastic article in the Florida Tech magazine. It's called "An Eater's Guide to Mars,"
Yep.
and you're in that, and it's great. So we'll make sure to put a link to that in the
Okay.
show notes.
Okay.
So
Absolutely. Yes.
so I guess I know a lot of the research concepts, a lot of the individuals that are involved with that, at some point they start looking at commercial endeavors because,
Mhm.
hey, my research my research is cool. It has some value and I think
Mhm.
there's commercial appeal to it. So
Mhm.
is that something that you've considered, or do you work more in a supporting role for groups that are doing the commercial side? What's kind of your objective with that?
Yeah, yeah. No, I love exploring fundamental science, but I do support if somebody is interested on this technology and they want to know what is the limitation of it and how to do the commercialization, etc. I do help them, and I work very closely with biochar producers as well as the hydrothermal carbonization industry who wants to, come into the business and then work with them because I do sincerely believe that I can do the research for the sake of research, but if that doesn't go to a commercialization, it doesn't go into the public eventually, that's going to be not that much of meaningful, at least in my opinion. So I do support. Every week I set up a couple of phone calls and meetings and talk to someone like I was talking to someone who is interested on like, okay, we have all those sargassum seaweed in
Hmm.
Caribbeans as well as in Florida. What to do with it? Can we make biochar out of it? What would be the quality of biochar? Can we actually sell it? So all these questions and what are the limitation of it. So I try to help them as much as I can, and also pointing out that what we can do. I also learn from them, like, okay, in order to push the commercialization, there are some questions or there are some risks that I need to de-risk it. So this is where my the research question come in, like, how do I de-risk this technology so that the commercial entity could actually make a decision and actually invest on it. So that's what I do. I don't plan to open an hydrothermal carbonization business. Maybe I'll change my mind, but yeah, so far I'm enjoying exploring my science and helping out to the community as well as the commercial entity.
Well, it sounds like you have this really fun puzzle around HTC materials and how you can make them and improve them, and you're thinking about both this world and other worlds, and so
Yeah.
and then the extra puzzles that you get to do that are really fun, and I can tell you're absolutely engaged in it, is when people say, "Hey, I have this thing, let's figure it out." And and you're just like,
Yeah.
"Yeah, I love to help." Yeah, so it's really refreshing to see that amount of enthusiasm and engagement. So, uh, I guess some of the things I guess I want to talk about is what do you see in the future for HTC? What are the advancements? project out, near term would be maybe 2030, longer term 2050 kind of. What do you see with that and maybe the HTC biochar connection?
Yeah, no, absolutely, absolutely. I think I'll start with HTC because the HTC, we are still, at least in the North America, we're still into like a large lab scale, and then probably a little bit about the pilot scale. One of the reason it hasn't picked up, in my opinion, is like there is no market for hydrochar established yet. I mean, you can go to Amazon and type biochar, and then there will be a lot of biochar producers and packed biochar come in. But if you type, go to Amazon, or you could go to Google and then ask like, okay, I want to buy a couple of bags of hydrochar, it is going to be difficult. I just submitted a proposal to USDA where I want to produce about a couple of tons of hydrochar to have a field demonstration and grow corn to it. It is difficult for me to get one, and then I think we have a commercial entity who wants to work with us, so we would probably be helping out each other and then get through it. So this is what I'm talking about. So we don't have a really established product that we could probably sell. So maybe by looking into commercialization as well as establishing the market would be a way to go for hydrothermal carbonization. And one of the other challenges, I would say, in terms of hydrothermal carbonization compared to pyrolysis, is like you can see pyrolysis can be done. I mean, if you are very cheap, you can still do pyrolysis. All you need is probably a big barrel, right? Big barrel, and then you can cut the barrel. You can do it relatively cheaper. But hydrothermal carbonization, because it is a high temperature, high pressure process, it is going to be more difficult. So it's usually more capital intensive. So that's probably one of the reasons where people hasn't come into it, because I mean, we have the application. They don't know how much they can sell and who they want to sell the product to, and also if they want to make a good decision or business decision on capital investment. So that's going to be a problem for hydrothermal carbonization sector. And looking into the other way is like, and it took pyrolysis industry a decent amount of time, but now you look into biochar now. And then they have so many different scales, and all they do is they do servicing, but they also sell pyrolyzer. So you can actually buy pyrolyzer from them to actually do it. And then air burners in Florida, they actually sell the pyrolyzer process commercially. But if you look into who sells hydrothermal carbonization reactor, not at least not in North America as of now. So that is going to be a challenge. I mean, it will overcome as long as you have a good market lined up, and it's going to work out. Now, for the pyrolysis, in my opinion, is like pyrolysis concept and biochar has been well established as a very good soil amendment as well as carbon sequestration, but it can have other applications as well. Once we start exploring more applications to it, then we are actually unlocking different markets for biochar. So different markets would actually increase the more demand for biochar, that would actually encourage the business to get into it. So I think what I expect to see is a new market actually opens up for biochar. For example, we need a good carbon source for battery material. So biochar could be one of them. We need good carbon source for for chips. and that could be one of them. We need biochar for water purification that we have been working on. So, many different. So as long as we have more and more applications comes up, because we established that the biochar is safe and biochar has already availability, as well as we already have a price point for biochar, but now we can push it for higher revenue as well as more niche market. We can do it. So this is what I'm expecting the biochar to be growing in the North America. But that's my opinion to it.
Yeah. Yeah. We already have about a dozen equipment manufacturers available throughout
Yep.
the US and overseas. And we're seeing rapid adoption and implementation of these systems, especially
Mhm.
with an energy generation power and
Yep.
thermal drying capacity. So
Hmm.
I guess what I'm hearing is that you're thinking maybe that 2030 we see like a more mature benchtop and small system
Yep.
HTC, and
Yep.
then maybe that 2050 we see us in the same position where we've got maybe a couple of dozen
Yep.
different types, and maybe we even have
Hmm.
something that you brought down from the space station that was being tested on
Yep.
the moon, right? And it's got your name written on the
Absolutely.
side. Wouldn't
Oh,
that
that
be
that
a
would that would
dream?
be a dream come
Yeah.
true. Yes.
Well, you put that engineering and carbonation material like experience and meld them together
No,
and come up with
absolutely.
something really cool.
Yeah.
So, I think in the market, it's pretty clear that PFAS remediation and mine site remediation, these things that deal with our everyday waste concerns, I, I think for me, that's what in listening to you, that's kind of what I hear is that we have some tremendous opportunities there as a way to deal with
Yep.
that feedstock and create the value. It's something we can't ignore anymore. So great opportunity. So if we have any junior scientists out there thinking about this right now, this is a
Hmm.
great path to go. There's going to be a lot of research that has to be done, a lot of opportunity,
Absolutely.
both for the brain and maybe even for the pocketbook if you can come up with some cool
Yep.
commercial product.
Absolutely.
I guess, let's see, what else is there about Mars? You know, what else is there about Mars that might be just like one extra thing we should be thinking about?
Well, I mean, well, so Mars has a lot of problems, but it has a lot of challenges as well. I mean, if you're thinking, if you give me a problem, I would probably think it as a challenge for me, and then provide you some solutions. So one of the things that we can do for Mars and the Moon is, how to enhance sustainability. We usually think that, the in Earth we actually start like, okay, we know how to let's make power, let's make fuel, let's make food, and then think about sustainability. And look where we are. But if we can do a better job now, because we are now thinking about growing habitats in Moon and Mars, so can we think it through? Can we think it through how to do sustainability? How do you do? Because when in Earth we have the landfill, whether you like it or not. In Florida, we have many.
Yeah.
There is no moonfill.
Yeah.
So what happened if you have a bag of garbage? Where does it go? So can you actually do it in moonfill? NASA has been thinking about it, but or maybe they do. But yeah, I mean, can we actually do it? So I think one of the thing that we think, or I think it'd be more and more happening is what we call the in situ resource utilization.
Hmm.
So it's in NASA's term, it would call ISRU, which basically be looking into like how can we reuse, recycle of material that we bring in, and we don't want to bring it back to the earth, but we can start reusing it, recycling it, as well as getting valuable material and product from what is available in lunar environment as well as Martian environment, and actually look at, for example, building materials. Can we actually tear apart the fabric that we grow? We bring it and then knit it over there in Mars. So we need a grandma in Mars and actually knitting it a sweater for me. But yeah, I think uh, something like that. So how can we do it? Can we actually do it? And then looking into sustainable habitat, I think this would be the way to go. And then, if we can start growing simple food, I think having something green would be very good for
Yeah.
for astronauts, and then actually harvesting those. I think that they would be very happy. You can imagine that.
Yeah. Who gets to eat the first Martian salad?
Yeah,
So, I mean,
exactly.
yeah, yeah, yeah. So, biochar is highly configurable. HTC is highly configurable. We have all these opportunities to deal with waste stream materials and carbonaceous materials and create benefit and value. I've worked on a project with a former NASA scientist, and she kind of blew my mind. And coming around to the fact that she said, NASA, you treat every molecule as precious. And
Oh
so
yeah.
it goes beyond that sustainability into the true circularity, because up there can be
Hmm.
no such thing as waste. So that's why you're leading the charge with HTC. It's like we have all this extra material, we have
Hmm.
energy opportunities, we can
Hmm.
start working on these harsh environments and looking
Yep.
at kind of that new frontier.
Yep.
So, all
Yep.
right. Well, I think I know you're busy. I know you're busy, and I'm keeping you there late past your end of day. So I do appreciate you making the time.
No
Let's
problem.
close up a little bit. If you had one thing to say, kind of as a message of opportunity, optimism, what's your influence? What could you say to an up and coming junior scientist that's interested in HTC Mars doing more with less?
Yeah, no, no, no. I think, yeah. So I think what my thinking would be like, the vision has to be big. So I want to solve a grand problem, but I should also have, not getting frustrated. I mean, you could probably not imagine how many times I have failed experiment. So and yeah, I mean, I learn from every time I fail. So it is absolutely fine. So you can have a failed experiment, but then that would strengthen your knowledge, that would actually prepare you to the next step. So having something, baby steps that we can do. I mean, for example, I mean, we have been looking into like, okay, I mean, if I mix Martian, regolith, and biochar, what would be the density of it? Okay, and also if I start leaching water to it, what am I leaching? What is the porosity that it's building? So it's just one thing, and then you'd basically be looking into like, can I grow something? Can I germinate something? How does it work under vacuum? Because the moon is a very high vacuum environment. So what would happen over there? What happened, reduced gravity. So if you throw someone with all those questions at once, and then they might actually get overwhelmed, like, okay, I don't know, I mean, this is like a too many unknowns for me, so we'll probably not be able to do it. My approach is like, okay, solve once at a time. These are the puzzle pieces, so you solve once at a time and then interconnect with each other, and then go beyond and actually do your. So you have to have uh, a vision, what we want to achieve, and also doing the baby steps towards the vision. And failure should not be a showstopper.
No,
You learn from
no,
your failure. You learn from your failure. But one thing I want to say is, if it is a failed experiment, it is very important to let the scientific community know that, okay, it
yeah,
doesn't
yeah,
work. So not try to hide it. I mean, I see a lot of papers looking into like, okay, I only publish if it works.
yeah.
That's very good. But then what you learned from your failed experiment, and then yeah, tell the scientific community that this didn't work, and I think I know that why it didn't work. So I think that this is going to be very important. That is going to be saved. Like, I spent 6 months for a failed experiment. I don't want somebody else to go through another 6 months to do the same thing and failed experiment. So scientists, we help each other. We That's how the knowledge will transfer, in my opinion.
Yeah, I completely agree with that. I've watched it happen in the biochar industry. You see a lot of the publications coming out, all positive, all positive. But let's celebrate those failures. Let's celebrate
Yep.
less than optimal results. And then let's act like a real community. Let's share that information.
Yeah.
Let's find a way
Mhm.
to prevent that from happening so we can focus on the true long-term value and opportunity with biochar
Yeah.
carbons and HTC products. So I guess what I heard from you for future scientists is be optimistic, look to the wide, big picture that you can participate in, and don't be afraid to focus on the little things, and then find a way
Yep.
to really chase that passion. Learn your math, learn your
Yep.
physics, maybe to practice a few languages. Like there's so much room for learning. So I think that, that's the kind of thing that I love to hear.
No, absolutely. I mean, I learn every day, and I learn from everyone. So it's I have an undergraduate working for me. I learn from him. I learn from her. So this is a good thing about academia and the environment. So yeah, I learn from everyone. I learned that the same problem can be solved in many different ways, and then somebody could come and tell me that yeah, it's just keep an open mind. Information will come. Do appreciate the information that coming, and the solution that is provided to us.
Let's let people, we'll include it in the show notes, but where should people look for you if they'd like to connect?
Yeah, no, absolutely. So yeah, we will have. So I have my research website, www.fit.edu /REZA. So you can look it up from there, and also in the chat, I will have the Google Scholar as well as my LinkedIn profile added to it. So if you have any questions, feel free to reach out to me. If you have any ideas, feel free to reach out to me. I'm only a small person, but I want to solve, and I am interested on tackling new challenges. I don't know whether I'll be able to solve it or not, but I can explore. I'm always happy to learn from you. I'd be
Yeah.
happy to listen to you. What you think?
Yeah, absolutely. We have so much. At some point, I'd like to have you back because I know we didn't cover your seagrass and the harmful algal bloom and a lot of your other research. So, but we're running long. So, again,
No
thank you,
problem.
and
No
thank you
problem.
for showing up. Thank you for your time. We look forward to great advances from you. Again, we'll include everything in the show notes. So, all
One,
right. So,
two, three.
Taufik, that was fantastic. So, uh, I got Mars on a photo. You've got the regolith there in person. So
Yes.
let's look forward to meeting and talking about this again. And let's look forward to human advances. All right. Thank you so much for joining us.
Thank you very much for having me.
Yeah,
Have a good day.
absolutely. You too. As we wrap up today's conversation, it is striking how carbon shows up not just as a soil amendment or as a climate solution, but as a bridge between worlds. Whether it is filtering toxins from our waters, supporting ecosystem recovery, or helping us imagine agriculture on Mars. The work of Dr. Reza reminds us that biochar and hydrochar are not static materials. They are highly configurable, engineered tools, alive with possibility. When we understand the chemistry, the biology, and the application context, carbon becomes a medium for solving problems instead of merely describing them. If humanity can grow food in the Martian regolith, then surely we can rebuild degraded soils here at home. We learned from Dr. Reza that we can use HTC process to help us with filtration, nutrient management, and even to address the growing PFAS and sewage sludge concerns, allowing us to heal and support the ecosystems we depend on. The research is challenging, the questions are complex, and the progress is rarely linear. But what we saw today is a future built through curiosity and persistent iteration. To everyone listening, the invitation is simple. Stay curious, stay collaborative, and keep looking at carbon, not as just as a material, but as a frontier. Big thanks again to Taufik, and we'll see you again soon on the Biochar Show. And to our listeners, thank you for tuning in. I know you enjoyed today's episode, and the best way you can support the Biochar Show is by subscribing on Spotify, Apple Podcasts, and YouTube. Be a true supporter and leave our podcast a 5-star review. It really helps others discover the show. And if somebody in your life would find this episode valuable, be a connector and share it with them. Thank you to Biochar Today for making this podcast possible. I'm your host, John Webster, with GoBiochar.com, your source. I am your source for bulk biochar supply throughout North America. See you next episode.